So okay, so we were here that we were talking about the vector spaces, and we've done all the properties of the vector spaces, and we've started that example, and where we want to show that this is going to be a vector space, and we proved first two properties, right? So now we're gonna prove one by one the additional properties and the multiplication property for the same question. So let's start with A1. So what was the A1? Let's back to the properties of this, properties of vector spaces. You see that A1 denotes the associativity among the vector space, right? So element should be associative under the addition. So we need to have three elements. So now we assume that U is U1, U2, V is V1, V2, and W is W1, W2. So now if you take U plus V plus W, so that means you are taking U1, U2 plus V1, V2, and you will add W1, W2 to this addition. It should be like U1 plus V1, U2 plus V2, right? So the first and the first component will be added, and second and the second will be added. Okay. So plus W1, W2. So again, if you have this component and this component, so first component will be added, and thereafter the second component will get added. So that will become U1 plus V1 plus W1, U2 plus V2 plus W2. So can I write it in this way that if I take U1, U2 outside, and if I can write it as V1 plus W1, V2 plus W2, can this be done? This is only because of the properties of the real number. We know that if we add the real number, no matter in which order we are going to add them, it doesn't make any difference, right? If we add 5, 7, and 9, doesn't matter if we add 5 and 7 plus or 7 and 9 plus, the resulting addition of these three numbers will remain same, right? So this is U, this is your V, and this is plus W, right? Yes. So we have started with this and we have reached over here. So that means the associativity holds in R2 as well. So let's come to the next property, and that is A2. And what does that A2 shows? A2 means there must exist a unique element, which we call it as zero vector, so that if we add this to any vector of V, it will not make any impact on this, right? So can you find any zero vector for this set V so that U plus that zero will remain U? Yes. Is there any zero vector? Let's say I have this U, which is coming out to be U1, U2, and I want to add zero into that. So what kind of zero can be added to this thing so that it will still remain U? Can you construct such zero?
0, 0.
Yes, very easy. 0, 0. Because if you add U1, U2, if you take U1, U2 and you add 0, 0 to that, it will still remain U1, U2, which will be U. Right? Okay, so अगर मैं R2 की बजाय, let's say in place of R2, I'm working with the R3, then U will look like what? U1, U2, and U3. And 0 will look like what?
0, 0, 0.
Bus. So it depends which kind of set we are working with, right? So on the basis of that, we decide our identity element. This is something which we call it an additive identity, right? You can also call this 0 as additive identity. Okay, so in this case, this is our additive identity, and set has this element. That's why the property number A2 is satisfied. right? So now let's go back to the A3. A3 means existence of additive inverse. So can you find for every u, can you find minus u so that u plus minus u will become 0? Can you do that? Yes. Can you add something to 2, 3 that it becomes 0? Tell me.
-2, -2.
Yes. Can you have something for this so that it becomes 0?
1 by √2.
1 by root
Yes.
2 minus root 3.
Okay. So that means every time we can do that. Yes.
Yes, sir.
Every time we can do that. Okay. So then we say that for every u, which is u1, u2, there exists minus u, which will be equal to minus u1 minus u2, such that u plus minus u will become R0 vector. That means for every element we have additive inverse. Is it fine? So for every u, we have additive inverse. Right? Yes, you're with me?
Yes, sir.
Okay, so let's say last property. Last property is what? Commutativity. So if you take u1, u2, and you take v1, v2, so can you tell me that u plus v will be equal to v plus u or not?
Yes, sir.
Yes, sir.
Definitely, because they are just numbers, right?
Yes.
Sorry. And we know that we can write it as v1 plus u1, v2 plus u2. Why? Because we are just dealing with the number. And this can be written as v1, v2 plus u1, u2, which can be further written as, this can be further written as v plus u. That means our property of commutativity holds, right?
Yes, sir.
Now, come back to this property, M1. What is that M1? Scalar multiplication. If we multiply alpha by u plus v, it should give you alpha u plus alpha v. So let's try to prove it. So let your alpha belongs to the R and your u and v belongs to the R2. So your u is u1, u2 and your v is v1, v2. Now try to solve the both sides. That means alpha times u plus v, alpha times u1, u2 plus v1, v2, which will be alpha times u1, v1, sorry, alpha times u1 plus v1, u2 plus v2. And this is something alpha u1 plus alpha v1, alpha u2 plus alpha v2. Can we write it in this way? Tell me.
Yes, sir.
Is it fine?
Yes, sir.
So further, it should look like alpha u1, alpha u1, alpha u2 plus alpha v1, alpha v2. Can we do this? Yes.
Yes, sir.
So further, I can write it as alpha u1, u2 plus alpha v1, v2. Is it okay? And finally, we can write in this way. So that's what we wanted to prove. Yes, fine. Can you see this property?
Yes, sir.
Yes, sir.
Right. And similarly, we can take two scalars and next we can prove this. So let's say how it works. So you talk about M2. This is your M2. right? And this is your N3. We'll be taking these two properties together and we'll prove those properties, okay? So now, for M2, so let alpha and beta belongs to the R and U is a vector belongs to the V. So alpha plus beta times U. That means alpha plus beta times what is U? U1, U2, a vector. So this scalar will be multiplied to the both component and scalar is in additional form, right? So we will write it as alpha plus beta times the U1, alpha plus beta times the U2. Okay. So further, we can write it in this form, alpha U1 plus beta U1, alpha U2 plus beta U2, right? Yes. ठीक है, ये प्रॉपर्टी है ना?
Yes, sir.
ठीक है, तो अब हमें प्रूव करना है इसे अल्फा यू प्लस बीटा वी. So for in order to make that alpha u beta v, you can write it as alpha u1, alpha u2. So break it component wise, beta u1, beta u2. So can I write it as alpha u1 u2 beta u1 u2? So that will become alpha u plus beta. Yes, सही है? Is it okay?
Yes, sir.
Yes, sir.
ठीक है, आसान है?
Yes, sir.
Okay, so see M3. And what is M3? Alpha beta u is equal to alpha times beta u. So let's try to find out this. Alpha beta u should be equal to alpha times beta u. So can we do this? Let's try. Alpha beta u1 u2 written as alpha beta u1 alpha beta u2, right? So you take the alpha outside, so this becomes beta u1 beta u2. Further you can write it as alpha beta times u1 u2 alpha beta times u. That's what we wanted to prove. Now we arrive at our last property. So you simply have 1 which is belonging to R. If you multiply 1 by this u1 u2, so that shall remain 1 times the u1 and 1 times the u2, that means u1 u2, so that will be equal to u. So therefore 1 into u is equal to u. Show that Rn is a vector space over R. Can you do this exercise?
सर एट टाइम्स आर क्रॉस आर ले लेंगे.
बस और कुछ नहीं करना है, सारा एक्सटेंशन हो जाएगा क्वेश्चन का, ठीक है? जस्ट फॉर प्रैक्टिस से Rn is nothing but R cross चलते चलते R कितने टाइम्स? n times. And each u will look like what? u1, u2 and so on up to un and so on. इसी तरह से चल, ठीक है? So exercise will be right on the path of this which we have done. अब एक करते हैं एक इंटरेस्टिंग क्वेश्चन. ओके, सो दैट इज 3 from exercise 3.1, right? So what we have given this thing. So V is given as to be R plus set of all positive reals, right? And the addition operation is now getting changed. That means whenever you take u plus v, you simply take the product of them, right? So uv belongs to the R positive. And what is the product operation, scalar multiplication wise, you take u raised to power alpha, right? For any alpha belonging to the R. Yes, what I'm trying to say is, see, doesn't matter addition means the usual addition, right? So new addition can be defined in this way, or there can be many other additions which can be defined, right? So it can be like this, u plus v minus 10. This can also be an addition operation. So this operation can be sort of customized, right? So this operation and this operation here, it's a sort of customized operations over here, right? Addition doesn't mean always that it has to be a usual addition. Okay, are you with me on this?
Yes, sir.
Yes, sir.
Now see that how things gonna change and how we'll prove each and every property, but this time things will get changed. So see how it works. So first of all, very first thing is what? That they should be closed under addition and scalar multiplication. And we shall prove that this set is going to be a vector space over R plus, right? So now, what do you take first? You take U and V, any two elements from R positive. So how the elements of R positive will look like? कुछ भी ऐसा जो positive real है, right? Something like 1 by root 2, 3, 7, 1 by 3, 5 by 9, something like that. Okay, so set of all positive real number is given to us. So our set is something like, so this is, let's say, 0, and we have this set. This is what we have right now. This is our R positive. Yes, is it okay?
Yes, sir.
So this is our R positive. Now see this. Now if you take U plus V, so here U plus V means what? U times V. So this U times V will again land in R plus or not?
Yes.
Bolo? Why?
Yes,
Because
sir.
this time plus has been converted into the product, right? So product of two positive number will remain always
Positive.
positive, right? So therefore, since product of two positive numbers is positive, therefore U plus V belongs to U plus V, which is, always keep in mind, this time it is U dot V, always belongs to the R positive. Now we want to think that whether the scalar multiplication is also coming, also satisfying this law or not. So if you take alpha U, this time alpha U has been defined as U raised to power alpha. So no matter if you take even negative value of alpha over here, so negative power will also indicate the reciprocal of a positive number, and reciprocal of a positive number will always be positive. So that's why U raised to power alpha also belongs to what? Yes, tell me.
R positive.
R positive.
R positive. Alpha is real, right? Keep in mind, alpha is real. Alpha is not R positive. Alpha can be any number. But if you take the power alpha, you take U raised to power alpha, no matter, even if it is negative power, it will only generate the reciprocal form. So if you take the reciprocal of every positive number, this will also be positive. Fine?
Yes, sir.
Yes,
sir.
you are with me?
Yes, sir.
Yes, sir.
Okay. So now let's now try to see the properties which we want to prove. So let's come up with the first property, that is A1. So that means if you take U plus V plus W, that should be equal to U plus V plus W. So let's try to solve this thing. Take the left hand side so that there should be no confusion. So this is given to us that U plus V is now UV. So if you again take the W into that plus W, so it will become UVW. And this is the product of numbers. So it doesn't matter, you take U and then VW. And this is nothing but U V plus W. Why? Because your product is addition over here. Yes. Is it okay? Fine, fair enough.
Yes, sir.
Okay. So what is your A2? Getting the identity element, right? So zero vector doesn't mean that it has to be zero. We are naming it, or you may call it as identity, additive identity, right? So how in this case you can find u plus zero, that should be equal to u. So in this case, what is your u plus zero? That means u dot zero should be equal to u. So what in place of zero, what can we write so that u times this vector should remain u?
1.
Huh?
Sir, 1.
Yes.
1.
Come on. बोलो सही बोल रहे थे बोलो.
1.
Sir, 1.
Exactly. One will replace this, right? And since we are taking the r positive only, so we have the number we have r only to the right hand side of the zeros, right? So there exists. So what we say by looking at this property, we say that there exists one belongs to the r positive, such that u plus 1, which will be equal to this time u dot 1, and which will be equal to u, right? So this time 1 is what? In this particular case, 1 is what? 1 is our additive identity, right? So here 1 is additive identity. Yes, fine.
Yes, sir.
Yes,
Bolo,
sir.
ठीक है? Now come to the A3. A3 states what? You need to have the associative, you need to have the additive inverse. So that means we need to find out, let's again copy that definition so that you can understand in a better way. So here you need u, for every u you need minus u so that it becomes identity 0. But identity in this particular case was what? 1. Yes. Is it fine? Okay. Tell me.
Yes, sir.
So in order to avoid the confusion, I replace this minus u. I don't know the value of this minus u. I call it as u dash. Right? But what is that u? What is that addition operation over here? That is this one. Right? It will get converted into the product form because that's what we have given. Okay? That's
Yes,
what we are given now. So
Yes.
now here u dash is what?
1 by u.
1 by u. So instead of minus u over here, in this particular case, we have additive inverse to be equal to 1 by u. Why? Because the additive thing has been converted into the product thing, right? So therefore, additive inverse in this case is 1 by u, A4. And that's what we want to prove. U plus v should be equal to v plus u. And that is quite obvious. Why? Because u plus v is equal to uv here, and uv can be written as vu, and vu can be written as v plus u. Right?
Yes, sir.
You're with me?
Yes, sir.
Yes, sir.
Okay. So let's get back to the multiplication properties. Now be careful that we're gonna use the multiplication properties, and we'll use the revised definition. So this is your first two properties. Now look into this, M1. You want to prove that alpha u plus v should be equal to alpha u plus alpha v. So what is alpha u plus v? So u plus v can be written as what? Tell me.
Alpha UV.
Yes, alpha uv. Yes, right. And alpha uv can be written in what form?
v to power u.
Huh?
v की power u.
uv raised to power alpha.
अच्छा.
Right? That's what given now. That's what the definition of product is. Scalar multiplication is given to us. Revised definition, sort of. Is it okay? Vector raised to power the scalar. Okay. Now take the right hand side. Alpha u plus alpha v. How can you write it then? Yes, tell me. Alpha u will be what? U raised to power. And alpha v is what? V raised to power alpha. And how the product operation is given to us? That should be u alpha times the v alpha. Right?
Yes, sir.
And this can be written as uv raised to power alpha. So left hand side and the right hand side are coming out to be same. Right?
Yes, sir.
So our M1 is satisfied. So let's now come to the M2. So now start with this. Alpha plus beta times the u should be equal to alpha u plus beta u. Alpha plus beta times u can be written in what form? U raised to power alpha plus beta. Okay?
Yes, sir.
Yes. Now you cannot write u raised to power alpha into beta. Why is it so?
Alpha beta scalars.
हाँ अल्फा बीटा स्केलर्स हैं वो वेक्टर के लिए ऑपरेशंस दिया है राइट नाउ कम टू द राइट हैंड साइड सो अल्फा यू प्लस बीटा यू सो यू कैन राइट इट एज u alpha times u beta u alpha plus u beta and again the plus operation can be written as u alpha times u beta. Now the base is same, so you can write it as u alpha plus beta. So left hand side and the right hand sides are same.
Yes, sir.
So M2 is satisfied, right? So now come to M3. So let's pick these last two properties. So M3. Now you want to prove alpha beta times u is equal to alpha beta u. So let's try to find out this. So left hand side, alpha beta u can be written as u raised to power alpha beta. Fine.
Yes, sir.
Yes, sir.
So how we should do this?
U
Then
beta times P alpha and then
Alpha times u ki power beta.
Yes. And now
U
u beta raised to power alpha.
alpha
So this becomes u alpha beta.
alpha beta.
Right?
yes, sir.
So the last one, 1 belong to the R, 1 times the U should be equal to U. Take 1 U, that means U raised to power 1, that will still remain U. Now you can say that R plus is a vector space over R under operations. Which operations? Which are given to us. That means u plus v should be equal to uv and alpha u should be equal to u raised to power alpha. Yes, you're with me?
Yes, sir.
So there are few more examples of vector spaces and this can be treated as exercises and you may check them. You may try to prove them that these are also the vector spaces. So that's it for today.